Let us see 2 points which should be clarified in the previous video. Now, the first one is about phosphorus acid. It is P with a lone pair connected to OH, and OH. Now, due to lone pair bond pair repulsion, this structure is unstable. So, this structure will try to remove the lone pair as a bond pair, and for that the OH bond will be shifting in its direction. This creates a double bond here, a pi bond here, and phosphorus gains the electron of hydrogen and a negative charge. So initially we get phosphorus with a lone pair, a negative charge, double bond O, then OH and OH, and then this H removed as H positive. Now this lone pair will be donated to H positive. Lone pair will become a bond pair. Now during that process, one electron is given to H positive, so its charge is neutralized, and since one electron is removed from phosphorus, its negative charge is also neutralized, and we get pH, double bond O, OH and OH. Now coming to the second point, that is reaction between alcohol and potassium iodide in presence of 95% phosphoric acid. Now there H3PO4 ionizes to give H positive and H2PO4 negative. Now ROH will get connected to H positive using the lone pair over oxygen, and we get ROH. Now this OH2 part, positive part, is the leaving group. Now it is a good leaving group because oxygen is possessing a positive charge, so it will strongly pull the electron pair towards itself from the RO bond. Now if R is primary, or ROH is a primary alcohol, then an SN2 reaction occurs between iodide ion. Iodide ion is obtained from potassium iodide ionizing as K positive and I negative. So I negative attacks ROH to positive by an SN2 path, producing a transition state I with delta negative charge bonded to R, bonded to OH, 2 with delta positive charge. So this is delta negative and delta positive. This is the transition state, and after the formation of transition state, this negative charge is completely gone for bond formation, and this partial bond is completely withdrawn, giving IR, alkyl iodide, and H2O. OH2 is H2O. And if R is a tertiary group, or ROH is a tertiary alcohol, then it is SN1 reaction where ROH2 positive ionizes as R positive and H2O. When this oxygen takes up this bonding pair of electron, the electron of R, that is carbon, is gained by oxygen. An extra electron neutralizes the positive charge over oxygen atom. Then this R positive will combine with the I negative, producing Ri. So now coming to what is called free radical halogenation. And free radical halogenation is started by ultraviolet light or heat. Now before studying free radical halogenation, we should know about the stability of free radicals. Now here we have taken isobutane. Then in presence of UV light or heat, the CH bond undergoes homolytic cleavage, and that is shown by an arrow, a curved arrow, but the arrow has only one head. We say it is a half-headed arrow, means the electron pair between C and H is equally shared between C and H, equally withdrawn by C and H, so that H gets one electron and C gets one electron. Now a species with one electron or an unpaired electron, a species with unpaired electron is called a free radical, and a free radical will possess a high energy because the energy needed for this breakage, that is energy needed for this homolytic cleavage, homolytic bond breaking, is taken up as the potential energy of this radical as well as hydrogen radical, which is not shown in the figure. Now this tertiary radical, this carbon which possesses the unpaired electron, is directly bonded to 3 other carbons, and then the CH bond directly connected to this carbon. So this carbon is directly bonded to this carbon and CH bond there. So we say the CH bond on adjacent carbon that undergoes homolytic cleavage, so that one electron goes to this carbon and one electron goes to this hydrogen. Now this carbon now will possess a p orbital with one electron, and again this carbon is possessing a p orbital with one electron. These two orbitals are mutually parallel, so that they will overlap to form a pi bond, and this H radical will be in combination with this system as a whole. So this unit as a whole will be one canonical structure, and since there are 9 CH bonds adjacent to this radical center, we have 9 such canonical structures, and this is similar to the carbocation, tertiary butyl carbocation, which possesses 9 hyperconjugation canonical structures. So a tertiary radical is more stable. Then coming to propane, the CH bond undergoing homolysis, we get this radical. It's a secondary radical called isopropyl radical. Now here we have 3 CH bonds here and 3 CH bonds here. So on the adjacent carbon to the radical center, we have altogether 6 CH bonds. So we have 6 hyperconjugation canonical structures. The CH bond undergoing homolysis. This carbon gains an unpaired orbital. This carbon also possesses an unpaired orbital. These two will overlap to get a pi bond. So this single bond becomes a double bond. Then this hydrogen as a radical will be in tight contact with this system, pi electron system, so that this acts as a single unit, and we have 6 such structures. So as the number of canonical structures decreases, the extent of delocalization of electrons decreases, and so stability decreases. When we come to ethane, UV light can produce the ethyl radical. Now ethyl radical is stabilized only by 3 canonical structures, because on the adjacent carbon there are only 3 CH bonds. This CH bond undergoing homolysis so that this carbon will possess an unpaired orbital, and this carbon possessing an unpaired orbital, these two orbitals will be mutually parallel, so they will overlap to get a pi bond, and this HRH radical is in tight contact with this pi electron system, and hence the primary radical is having the least number of canonical structures, and the primary radical, free radical, is least stable. So the stability of free radicals is in the order tertiary greater than secondary greater than primary. Now coming to free radical chlorination, we take the example of butane. Now one speciality with butane is that this is a CS2 group. For showing the reaction, I am writing this CH as C bond H, but this is a CS2. Now place a mirror here. This CS2 is away from the mirror to a particular distance, and this CS2 is also at the same distance away from the mirror, and this CS3 is away from the mirror at the same distance as this CS3 is away from the mirror. So this is the object portion and this is the mirror portion, so that this molecule is symmetrical, so that this CS3 and this CS3 are similar, this CS2 and this CS2 are similar, so that when chlorination occurs to this molecule, we can have one chlorine here and one chlorine here. One chlorine here or one chlorine here will give the same isomer. One chlorine here or one chlorine here will give the same isomer. So two only monochloro derivatives are possible for this structure. Now, in presence of ultraviolet light during chlorination, chlorine molecule undergoes a homolytic cleavage, and we get two chlorine radicals, free radicals. Now there is an equation, a radical 1 plus molecule 1 giving radical 2 and molecule 2. So this molecule, that is N-butane, undergoing homolytic cleavage to give H radical and so much as a radical. Now chlorine radical reacts with this molecule. So radical 1 is chlorine radical and molecule 1 is N-butane. The CH bond undergoing homolysis, we get one electron in an orbital over this carbon, and a hydrogen will possess one electron in its orbitals. Now hydrogen with its electron in the orbital, it is similar to hydrogen atom. Only thing is that it is having the potential energy needed for a homolysis of this bond, so it is at a high energy condition. Now this hydrogen as a radical will combine with the chlorine as a radical, then we get HCl molecule. Now during bond formation, energy is released, so that the potential energy of hydrogen free radical and chlorine free radical are removed as the bond formation energy and alveolar formation of the bond. So the potential energy of the system is lowered because bond formation is exothermic in nature. Then we get a CH group containing carbon with an unpaired electron. So a radical plus a molecule giving another radical and another molecule. Now the same pattern is followed by this radical. This radical reacts with a chlorine molecule. Now chlorine molecule undergoes homolytic cleavage, and a chlorine radical and a chlorine radical, two chlorine radicals are created. One chlorine radical combines with this carbon, so that the single electron orbital of this chlorine overlaps with the single electron orbital of this carbon, producing a CCl bond. Now this chlorine radical is left free. That chlorine radical can react with another butane molecule, and the reaction can proceed in this manner. and such reactions are called chain reactions because they will go on because chlorine radical, that reactive radical, is produced in each step of this reaction. Now suppose the end carbon atom, the methyl carbon, is undergoing homolysis of the CH bonds, then we get H radical combining with the chlorine radical. So in presence of chlorine radical, this molecule undergoes homolytic cleavage, obeying the equation radical 1 plus molecule 1 giving radical 2 and molecule 2. So we get radical centered here, and this H radical created here combines with the chlorine radical producing HCl molecule, and this radical can react with another chlorine molecule undergoing homolysis, so that this chlorine radical will combine with this radical, alkyl radical, then we get a Cl bond, then a free chlorine radical. This can react with the again and butane molecule like this, or this molecule, the same molecule at this point or at this point. So that reaction will proceed further. Now coming to an isomeric structure. Now this one is, we can number the carbon atoms as 1, 2, 3, 4, so that it is 2-methyl butane. Now it is asked how many monochloro derivatives are possible for this structure. Now you place a mirror along the dashed line, then we get this methyl group as the image of this methyl group. So these two methyl groups are similar with shape. So when a hydrogen atom is removed from this methyl group by a chlorine atom, or from this methyl group, we get the same monochloro derivative. So that forms one monohalide derivative. So these two methyl groups are similarly placed. Now this is a secondary carbon and there is a hydrogen. So this hydrogen may be replaced. This carbon is a tertiary carbon because this carbon is directly bonded to 3 other carbons. It's a tertiary carbon. Carbon 2 is a tertiary carbon. And this hydrogen may be replaced by a chlorine to get another isomer. So first isomer obtained by replacing the hydrogen from this methyl or this methyl, both are the same. And then this is a tertiary carbon. So you replace this hydrogen by a chlorine, we get a second isomer. And this is a secondary carbon because this carbon is directly bonded to 2 other carbons. So replacement of one hydrogen by a chlorine, we get a third isomer of the monochloro derivative. And this is a primary carbon, and this is also a primary carbon, this is also a primary carbon. But this methyl is connected to a CH group and this methyl is connected to a CH group, whereas this methyl is connected to a CH2 group. So the surrounding of this methyl is different from the surroundings of these two methyls, so that from this methyl, when one hydrogen is replaced by a chlorine, we get a fourth monochloro derivative. So replace one hydrogen by a chlorine from here, replace this hydrogen by a chlorine, replace one hydrogen by a chlorine, replace one hydrogen by a chlorine. So we get 4 isomers. So 4 monochloro derivatives are possible for 2-methyl butane. Then as an example, this molecule is called neopentane. It's an isomer of pentane. Now especially with the neopentane, see, neopentane will be having such a structure. All these green balls are methyl groups. Now a plane passing through these methyl groups and the carbon, this plane, so this plane passing through this methyl group and this carbon, and again this methyl group, if this is extended. So such a plane passing through the methyl groups and carbon, we get these two methyls as the images. But in the figure we can show this. Suppose a mirror is placed here. These two methyl groups are object and images. So these two methyl groups are similarly placed. Suppose another mirror is kept here, then these two methyls are similarly placed. So in fact, all these methyl groups are equivalent or similarly placed, so that this structure can give only one monochloro derivative. That is, you replace any one hydrogen of the four methyl groups, you get the same isomer. So CH2Cl, you can replace the hydrogen here, ACH2Cl, or here ACH2Cl, or here ACH2Cl. All these monochloro derivatives are the same, so only one isomer possible. Now for a dichloro derivative of neopentane, you can replace two H atoms from this carbon by 2 chlorine. So that is shown here, CHClCl. Or better, you can replace one H atom from one methyl and the other H atom from any one of the methyl group, because all these groups are similar. So you can replace a second hydrogen from this methyl or from this methyl or from this methyl, we get the same isomer. So CH2Cl, CH2Cl, or CH2Cl, CH2Cl, or CH2Cl, CH2Cl, all are the same molecules. So one monochloro derivative and one dichloro derivative are possible. One monochloro derivative and two dichloro derivatives are possible for neopentane. The two dichloro derivatives are CHCl2 and CH2Cl, CH2Cl. So these are the dichloro derivatives, and only one monochloro derivative is possible for neopentane. Now then, preparation of alkyl halide from alkene. So addition of HBr or HCl to a double bond. Now the pi bond here breaks, producing two valencies over these carbon atoms. HBr bond breaks, producing one valency over H, one valency over Br. The valency produced over carbon combines with the valency over hydrogen. The valency produced over this carbon combines with the valency of this bromine. Or it can take place in the other way. The valency created here will combine with the valency created over bromine to form a CBr bond, and the valency created over this carbon combined with the valency created over hydrogen to produce a CH bond. Now the nature of these addition reactions is decided by a rule called Markownikov's rule, which was studied previously, and this rule states that the negative part of the addendum, that is, this is the addendum molecule, goes to the carbon. The negative part is bromine, goes to the carbon connected to the least number of hydrogen atoms. Now we can take the example of propane. There are two unsaturated carbons, we can say this is carbon 1 and this is carbon 2, both are unsaturated. Now when an unsymmetrical alkene, this alkene at the position of the double bond, you place a mirror, these two are not related as object and image structures. The alkene is unsymmetrical because CH2 is not the image of CH3CH. Again, H is not the image of Br, so HBr, which is called the addendum, is unsymmetrical, and the alkene is also unsymmetrical. When an unsymmetrical alkene adds to an unsymmetrical addendum, it is given by Markownikov's rule that negative part, that is found here because it is more electronegative. Negative part of this addendum goes or bonds to the carbon, to the unsaturated carbon connected to the smallest number of hydrogen atoms. So that will be the major product during the reaction. This is the major product, so that the negative part is getting connected to that unsaturated carbon connected to the least number of H atoms. And the minor product will also be formed to some extent. Now here, initially, HBr ionizes to H positive and Br negative. Now HBr, being an electrophile, attacks the alkene structure. You might remember the electromagnetic effect. Now HBr coming from this side, the pi bond will be shifted towards this direction, so that a bond will be formed when between this carbon and this hydrogen. So this CH2 bond CH becomes CH3, and we get a positive charge on this carbon, so a positive charge. Now this is a secondary carbocation because the positive carbon is directly bonded to two other carbons. Now this is more stable. Now suppose H positive is coming from this side, that is the left hand side. This pi bond will be shifting in this direction to form a sigma bond between this carbon and H positive, so that this group becomes CH2, this bond becomes a single bond, and this becomes a CH2 with a positive charge, because the electron pair when moves in this direction, the share of this carbon is lost to the hydrogen. So hydrogen neutralizes its charge. This positive charge is created over this carbon. We get a positive carbon in which the positive carbon compound ion, a carbocation, in which the positive carbon is directly bonded only to one carbon. So it is a primary carbocation. This is a secondary carbocation. A secondary carbocation is more stable than a primary carbocation, because there are 3 plus 3, 6 hyperconjugation canonical structures, and the inductive effect of two methyl groups which can share this positive charge, whereas only here there are two hyperconjugation canonical structures and the methyl group transmitted through this carbon chain. So this is less stable, so that this is formed to a lower extent. If this is 80%, it will be only 20%. Then in the second stage, a fast stage where the carbocation combines with Br negative, both carbocations, we get this product, that is 1,2 bromopropane and 1 bromopropane. 2 bromopropane is the major product and 1 bromopropane is the minor product. So this is major because this carbocation is the major carbocation and this is minor product. So the addition follows Markownikov's rule. And there is another phenomenon called Karash effect or peroxide effect. In presence of a peroxide, the addition is against Markownikov's rule or anti-Markownikov's addition occurs, and this starts with a peroxide. So the reaction is a free radical reaction initiated by light. Now there is a peroxide called benzoyl peroxide. Benzoyl group is C6H5CO. C6H5CO. This linkage O bond O with the two valencies is called peroxide linkage. So this compound as a whole is called benzoyl peroxide, which is commonly used for such reactions. Now, in presence of light or heat, HNU ultraviolet radiation, benzoyl peroxide undergoes homolysis. We can show it by only one half-head arrow, or we can show both arrows, no harm. If there is only one half-head arrow in this direction, there is no harm. But here I am showing the reaction by two half-headed arrows. Both are the same. You can use only one half-headed arrow or two half-headed arrow. Now we get oxygen atom with a single electron, that is a free radical. Then again you remember the general reaction, radical 1 plus molecule 1 giving radical 2 and molecule 2. So we get benzoate radical, that is R1, and HBr molecule. We get HBr being homolyzed to H radical and Br radical. This H radical combines with the O radical, so that this half-filled orbital combines with the half-filled orbital of hydrogen, producing OH bond. This is benzoic acid. And we get a free bromine radical. Now that free bromine radical will react with this unsymmetrical alkane. Now we can call it 1, 2, 3, 3 phenyl, 1 propene, where propene is the parent compound. So you need not remember the name of the compound, just understand the reaction. Now when this unsymmetrical alkene reacts with bromine radical, see, during the homolytic cleavage of this pi bond in this direction, or better in this direction, we get a radical center here. So initially the homolytic cleavage occurs in this direction, so that a radical center is created here and a radical center is created here. Now the bromine radical can combine with this center or this center. Suppose the bromine radical is combining with this radical center, so that the unpaired electron over this carbon in an orbital overlaps with the unpaired orbital of bromine, producing a sigma bond, so CS2Br, so that the radical center becomes here. So the unpaired orbital with a single electron becomes here. This is a secondary carbon, which can be stabilized by hyperconjugation, and then we get the final product, where this radical combines with a molecule to produce another radical and another molecule. So this radical combines with the HBr molecule, which undergoes homolysis to produce Br radical and H radical. H radical combines with this radical center, producing CH bond, CS2, and there is already a bromine present, plus we get the Br radical. So satisfying the general reaction, radical 1 plus molecule 1 giving radical 2 and molecule 2. So always during free radical reaction this equation is obeyed. Suppose the homolysis is occurring in the opposite direction, and the Br radical gets connected here. We get a primary radical which is less stable, and there is only one hyperconjugation canonical structure possible for this one, because there is only one CH bond adjacent to this carbon. So it's a primary radical, free radical, which is less stable than a secondary free radical. Now this radical reacts with a molecule of HBr, producing another molecule and another radical. So much about free radical fluorination or halogenation, or domination or halogenation. Now coming to another reaction, a named reaction called Finkelstein reaction. Now here an alkyl halide is treated with a sodium iodide in a less polar medium, a non-polar medium, that is dry acetone. Now the alkyl halide can be alkyl chloride or alkyl bromide, and sodium iodide. Now iodide ion is a good nucleophile. Because of its large size. So iodide ion is large in size. We get the nucleus here, I negative, and this is the electron cloud. Now since this distance is very great, the outermost electron cloud may be easily distorted by a positive ion coming near the iodide ion. See, in a case of a CCl bond, we have a delta positive and delta negative chlorine. Now this delta positive carbon can easily distort the electron cloud of a large iodide ion because the nucleus is far away from the external electron cloud part. Now the ability of a positive ion, fully or partially positive ion, to distort the electron cloud of a negative ion is called power of polarization. So power of polarization or polarizing power, it is called, is the ability of a positive atom to distort the electron cloud of a negative ion. So the atom may be partially positive or a fully positive ion, and its power to distort the electron cloud of a negative ion is called the power of polarization or polarizing power. Now in the converse direction, the susceptibility of the negative ion to yield means valanguka. The susceptibility of the negative ion to yield to polarizing power or power of polarization is called polarizability. So here iodide ion yields to the polarizing power of positive carbon, partially positive carbon in an organic halide. Now iodide ion is highly polarizable because of its large size. So its electron cloud may be easily distorted by positive carbon, and this favors bond formation. And hence we say iodide is a better nucleophile. So iodide is a good nucleophile due to its high polarizability. High polarizability. Now, a Finkelstein reaction is a reversible reaction, and the dry acetone is a less polar medium, and polarity is decided by the dielectric constant of the medium. For acetone it is about 2, for water it is 80, so we can consider water as a highly polar solvent, whereas acetone has practically a non-polar solvent. Now, dielectric constant is the property of the solvent to hold the ions separately in the medium, hold the ions from coming into contact. So they resist the combination of ions in the medium, oppositely charged ions in the medium. So that a solvent of low dielectric constant cannot hold the ions separately, or ionization cannot be favored in a solvent of low dielectric constant or low polarity. Now the reaction is Rx plus NaI, giving you put the X and Na in a box, so NaX is formed. Now since it is a non-polar medium, this ionic compound cannot exist as free ions because it is less polar. It cannot hold the ions separately, so that ions will combine and will form a precipitate. If X is Cl, we get NaCl as a precipitate. If X is Br, we get NaBr as a precipitate. And when NaX or NaX, that is NaCl or NaBr, is precipitated, it is removed from the equilibrium, and so the forward reaction is favored. We get alkyl iodide. So triacetone is important because it is a non-polar medium, and in that medium this reaction occurs in the forward direction because NaX is removed from the site of equilibrium. So as you remove the product from the site of equilibrium, forward reaction is speeded up. Now one drawback of this reaction is that only primary alkyl halides react by Finkelstein reaction. Tertiary alkyl halides will undergo hydrolysis, that is formation of ions, carbocation and halide ion in the medium. So ionization of the alkyl halide molecule is required for SN1 reaction, but since acetone is a less polar medium having low dielectric constant, it cannot favor the formation of ions. So SN1 reaction is absent in acetone, triacetone. So Finkelstein reaction does not favor SN1 reaction. So that tertiary alkyl halides do not react by Finkelstein mechanism. So we cannot use a tertiary alkyl halide for a Finkelstein reaction. We can use only primary alkyl halides, and that is because triacetone is a less polar medium. It will not favor the rate determining step of SN1 reaction, that is hydrolysis or ionization of the alkyl halide. Now coming to another reaction, that is Schwarz reaction, which is used for the preparation of alkyl fluorides. Now the reagents used are silver fluoride AgF, Hg2F2, COF2. All these are compounds of transition metals, SbF3, which contain vacant orbitals. So all these transition metal compounds and SbF3 possess vacant orbitals into which a lone pair of the halogen may be accepted. So a lone pair of halogen is accepted, then fluorine is getting free, and then fluoride ion will attack by an SN2 mechanism. Here the leaving group is dispersed and FCH3 bond is formed along with the AgBr. And if the alkyl halide taken is a tertiary alkyl halide, then we can have a tertiary carbocation by hydrolysis of this bond in the absence of fluoride, so that we get the corresponding carbocation. It is, if you take tertiary alkyl bromide, you will get a tertiary carbocation, and then it can react with fluoride to produce the corresponding halogen derivative. So much. Thank you.